A very good morning to our instructor, Dr. Norazana. We are from group number 6. I am Emma Surya Skolian and the group leader for the second experiment. My group members are Ganwei Teng, Amirul Hakim, and Dana Silan. For today's presentation, we will share our findings in flow measurement. The abstract. The aim of this experiment is to determine and compare the discharge of different types of flow measurement methods, which are orifice plate, venturi, and nozzle. Different value of inlet and outlet is recorded when the water level is at minimum and maximum. Theoretical flow rate is calculated by using Bernoulli and continuity equation. And in conclusion, the most accurate flow meter is venturi meter. Our main objective for the second experiment are to measure the flow of water using different flow meters, which are orifice plate, flow meter, nozzle, venturi meter, and rotameter, by applying Bernoulli's principle. Next is to determine and compare the discharge coefficient of different types of flow measurement methods. Third is to investigate the relationship between water level in manometer and pressure drop. And lastly is to calibrate the flow meters. Introduction. Bernoulli has discovered the relationship between pressure and velocity of a fluid flowing in a pipe. Bernoulli principle states that increase in liquid speed creates a pressure decrease and vice versa, which is meant by when pressure is high, velocity will be low. Most of flowing measuring device applied Bernoulli equation. In this flow measurement experiment, we will use common type flow meters named as orifice plate, nozzle, and venturi. Each of these meters operate on the similar concept, and water will be used as flowing fluid medium.
Okay, hi everyone. My name is Dana, and today I'm going to talk about the theories of this experiment. So, first, we are going to take a look at the Bernoulli's equation itself. So, Bernoulli's equation is, as you can see, P1 plus 1 over 2 rho V1 square plus rho GH1 equals to P2 plus 1 over 2 rho V2 square plus rho GH2. So what these equations represent is, this equation itself, it represents the energy balance within a energy balance of a fluid flowing through a pipe. So as you can see, pressure is the energy from the pressure, and then 1 over 2 rho v1 square is actually the kinetic energy, and then the rho gh, as you know, is the gravity, I mean not gravity, potential energy. So so now, since we assume in this experiment, we assume that the pipe is is what is the same height. That means the h1 and h2 is same. So we can cut off rho g h1 and rho g h2. So then we'll end up with this equation here. It says P1 plus 102 rho V1 square equals to P2 plus 102 rho V2 square. So from this equation, we can easily conclude that P and V are inversely proportional, which means as velocity of the flowing fluid increase, the pressure exerted by that fluid is it will reduce. So then we are going to take a look at the second equation. So the second equation is the continuity equation. So it says A1 V1 equals to A2 V2. So what it states is it states that the velocity of a fluid flowing through a small cross-sectional area is high compared to the velocity of a fluid flowing through a big cross-sectional area. So imagine if a fluid is flowing through in a pipe with a lesser area, a small pipe, the fluid will actually move faster than it would move in a pipe that is big, that has a larger cross-sectional area. So from those from those theories that we just discussed, we can conclude that for this scenario, A2 is bigger than lesser than A1. So as you can see here, this is 0.2. So the area here is lesser compared to here. So which means the velocity of fluid at this point is bigger than this point. And when velocity is higher, that means the pressure drops. So the pressure 2 is lesser than pressure 1. Alright. Now, in this experiment, we use the theories we concluded before to compare the discharge coefficient of different types of flow measurement methods. So what is discharge coefficient? Is actually the actual flow rate over the theoretical flow rate. Alright, so for years many types of devices have been developed using Bernoulli's principle from the equation to measure the velocity and flow rate. Velocity as spelling mistake. It's okay. To measure the velocity and a flow rate. So in this experiment, we are going to take a look at the three particular devices, which is orifice plate, nozzle, and venturi. So their operation is almost based on the theories we discussed before from the equation of Bernoulli and the continuity equation. So now we are going to take a look at the description of these flow meters. So first is orifice plate. So an orifice plate is a restriction with an opening smaller than the pipe diameter, which is inserted in the pipe as depicted in the figure. So this is the orifice. As you can see, there's a restriction at the point 2, and due to smaller openings in the area, the fluid velocity will increase, and hence causes a decrease in pressure. The flow rate can be calculated from pressure drop across orifice P1 minus P2. So as you can see here, there is a restriction, and the area here is smaller. So that means the velocity of the fluid here is higher compared to the point 1. So this causes the pressure to drop, and you can calculate the difference in pressure by the equation that P1 minus P2. And here they say that Z1 equals to Z2. It's actually height. So we assume that it is the level is same for both points. And then as you can see here, there's quite a bit of a turbulence here. So this orifice causes a lot of turbulence. It is not a very effective method. So the equations for theoretical flow rate QTH can be expressed as the following. So this is the equation to find the theoretical flow rate. So here's the equation to find the difference of pressure from point 1 to point B. So this is the equation to find the coefficient of discharge, which is actual flow rate over theoretical flow rate. So this actual flow rate we will get it from the experiment itself, from the rotameter. Alright, and now we are going to look at the second device. So the second device is the nozzle applied. The nozzle. So the nozzle applies the same principle and calculation like we discussed earlier as the orifice plate, and the only changes is the area at number 2. So as you can see from the previous picture, here the turbulence is not so bad. It's not good, but it's not so bad at the same time. But as you can see here, the turbulence is very bad, right, compared to the first one. Now we are going to take a look at the venturi. So the venturi consists of a rapidly converging section. As you can see, instead of having a restriction, they reduce the size of pipe itself. They reduce the cross-sectional area of the pipe, the shape of the pipe. It converges, as you can see here. So here the speed will increase since the area is lesser, and the pressure drops here, and which increases the velocity, as I say, and hence reduces the pressure. It then returns to the original dimension of the pipe by a gently diverging diffuser. So this is a diffuser. As you can see, this is the earlier area of the pipe lah, and it returns to the same area, but over a diverging diffuser. So why they did this? They did this because it is actually effective in reducing the turbulence within the pipe, right? So we can measure the pressure differences, and discharge coefficients can be calculated, and this is a very accurate method of flow measurement, as energy loss is very small because there's no turbulence, so there's no much energy loss. So next we are going to take a look at the methodology of this experiment. So how do we conduct this experiment? So first we are going to conduct the experiment using orifice plate. So we have to fix the orifice plate properly, and then we must ensure that the manometer tubes H1 and H2 are fastened. So why? Because we are using water as the flowing fluid, so water can leak, so we must ensure that they are fastened to avoid any kind of leakage. And the leakage can cause difference in readings. So second we have to do is we must close the flow control and gate valves, and then the main switch in the pump was turned on. Alright, and then the flow control and the gate valves were slowly opened simultaneously until they reach their maximum opening level, which means until the water in the manometer overflows. So we are going to slowly open the gate valve and the flow control simultaneously, and we are going to do it until the water in the manometer overflows. So the fourth is we open the ventilation valve. So why do we open the ventilation valve? Because there are some gas bubbles and they can cause they have pressure, so you need to release the pressure in order to actually get a proper reading. The bubbles can mess up our reading. So the fifth is we closed the ventilation valve back, and then the gate valve was closed, and then the pump was turned off. So the sixth is the ventilation valve was slowly opened, the white one was slowly opened until the minimum water level, which is 30 to 40 millimeter, was reached, and then the pump was turned on again. And number 7, we have the gate valve was slowly opened until the level of water in H1 reached maximum 390 mm, and then the manometer H2 was at a minimum level. So all the readings H1, H2 and the rotameter actual flow rate was recorded, and then all the readings were recorded, and then we are going to take 5 different readings. How are you going to adjust the actual flow rate? Is by opening the gate valve. So adjust the opening of the gate valve lah. So we will take the results for 5 different values of actual flow rate. And then number 8, the gate valve was closed and the pump was turned off, and the manometer tubes H1 and H2 were removed from the orifice plate. So at this point the experiment for orifice plate has finished. So we're going to change it with nozzle. So we are disconnecting the H1 and H2 and we are taking out the orifice plate. So now the orifice plate was changed with the nozzle. So the step 1 to 8 was repeated. Meanwhile the venturi, for the venturi, the manometer tubes were connected to H1 to H3. And similar steps of 1 to 8 was applied. Alright, so all the manometer tubes were removed from the system and the flow control valve was closed. The pump and main switch was turned off after the steps were finished. So basically after we've done everything, we close all the pumps and flow control valve and we turn off everything, and the experiment is over. Thank you.
This is the results for the experiments. The actual flow rate for each type of flow meters is calculated by using the volume of water collected divided by the times and convert the units into meter cube per second. The theoretical flow rate is also calculated by using the Bernoulli equations. And next, in order to get the discharge of coefficients for each type of the flow meter, the actual flow rate is divided by the theoretical flow rate. Discussions. The first discussions is the differences on water level in manometer with different types of flow meter. So based on the results obtained, we can observe that the value of H1 is always greater than H2 for all types of flow meter. The differences on water level can be explained by looking at the equation of continuity, which is the Bernoulli equations. P1 over rho g plus V1 squared over 2g plus tech 1 equal to P2 over rho g plus V2 squared over 2g plus tech 2. And since there is no difference in Z in the flow meter, hence the equation becomes P1 over rho g plus V1 squared over 2g equal to P2 over rho g plus V2 squared over 2g. And also according to the equations Q equal to AV, and since A2 is smaller than A1, hence V2 is greater than V1. And when V2 is greater than V1, the pressure losses occur, which is pressure 2 less than pressure 1, to ensure the Bernoulli's equations has to be balanced. And this has proven that YH2 is always lower than H1 in all the flow rates. The second discussion is the differences in discharge coefficient value for each of the flow meter, and the ranking of the flow meter according to their accuracy. So, the average coefficient of discharge for each type of flow meter is determined. So we can see that the venturimeter has CD value of 0.9607 and Ehrenfest plane has the lowest CD value, which is 0.6849, while nozzle exhibits the highest CD value of 1.0543. The higher the value of CD, the higher the accuracy and closer to the reading of unity, but does not exceed 1. The CD is less than unity when there are losses caused by the wall shear stress, the losses in contraction, and the losses during expansions. The greater contraction and expansion of the venturi prevent flow separation and swirling, and it suffers only frictional losses on the inner wall surfaces. Hence, from here we can know that there are low head losses in venturimeter due to its fast recovery. And for the Ehrenfest meters, it has significant head losses or permanent pressure losses due to its sudden change in its flow area, which can cause considerable swirl. And for nozzle meters, the plane is separated by a nozzle and the flow in the nozzle is streamlined. The frictional losses in a flow meter are much less than in an Ehrenfest meter, but higher than venturimeter. So based on that, we can know that the most accurate flow meter is venturimeter, and this is because the CD value of venturimeter is very high and does not exceed 1 compared to the nozzle, which the CD value is just marginally exceeding 1. The friction loss that produced by the venturimeter was lower than the Ehrenfest plane meter and nozzle due to the difference in geometrical structure. And since the CD value of nozzle is the highest and just marginally exceeding 1, we can conclude that the accuracy of nozzle is lower than venturimeter but higher than Ehrenfest meter. The CD value obtained for nozzle shows that there might be some errors when conducting the experiments because the actual flow rate is higher than the theoretical flow rate. So we can conclude that the venturimeter has the highest accuracy and Ehrenfest will have the lowest accuracy. Next is the factors contributing to errors or inaccuracy in experimental data and the possible recommendations to improve the existing results. So here we got 3 factors that will contribute to errors. The first one is the presence of air bubbles in the connections of flexible tubing and manometer. The second will be the human reaction time towards visual or sound stimuli. So for example, when pressing the stopwatch to start or stop the time, the reaction will be different from human to human, and for each human, his or her reaction will be different from one experiment to another experiment. The stopwatch may have been stopped too soon or too late, and either way will affect the readings. And next is the parallax error. The error may occur when reading the water volume scale and manometer, which means that the eye level to read the reading is not at the correct positions. And for the recommendations is to check thoroughly and make sure that the connections of flexible tubing and manometer are free of air pockets. Second, the parallax errors can be minimized by viewing the reading at eye level at the meniscus. Means that the observer eye level must be perpendicular to the scale that needs to be read. And next is to clean the apparatus before conducting the experiment to make sure it is in good shape and the accuracy of the data can be increased. And last is to repeat the experiments few times, get more data measurements for each readings and find their average.
Hey everyone, I will cover conclusion and recommendation part. For the conclusion, definition of flow rate is the quantity of a gas or liquid that passes through a pipe per unit time, typically expressed by the symbol Q with the cubic per second in the SI unit. In the experiment, flow rate was measured by using Knudsen meter, meter, and Oliphant meter. The purpose of the experiment is to determine and compare the coefficient of discharge for a series of flow measurement devices, which are meter, nozzle, and Oliphant split meter. The result we get as below. For meter, CD value is 0.9607, nozzle meter 1.0543, and last meter is 0.6849. Based on the concept, when the velocity of flow rate is increased, the pressure in the fluid is decreased. So it can be said that measurement device that we study above are function based on Bernoulli concept. From the data obtained and we get the average CD for meter has 0.9607, while meter has the lower CD which is 0.6849, while nozzle meter has highest CD value of 1.0543. Because the Oliphant meter has suction head losses or component pressure losses that can cause considerable swells. The plate is divided by a nozzle in the nozzle meter and the probe in the nozzle is streamlined. In flow nozzle, the frictional losses are much less than in Oliphant meter but higher than a meter. Since the CD value of nozzle meter is slightly greater than 1, the accuracy of nozzle meter can be inferred to be lower than meter but higher than the Oliphant meter. The CD value obtained for nozzle suggests that when we performing the test or experiment, there might be some errors that actually flow rate is higher than the theoretical flow rate. Okay, for the recommendation, there are some ways that we can use to reduce error based on the experiment. First of all, we have to research the manual lab we have been provided before we run the experiment. So we can run the unit and the procedure smoothly and completely understand them. We will also double our skill and experience to ensure that the test can be carried out smoothly. For improved accuracy, we need to ensure that there are no air bubbles and to prevent error in readings. Check and make sure that the connection of flexible tubing and manometer are free of air bubble. Take time to allow air bubbles to escape. Next, to prevent parallax error, we should our eyes should as perpendicular to the eye level of the readings from the manometer to get the accuracy reading. To get the correct data and result, we need to avoid parallax error. Last but not least, to get a more accurate result, the measurement should be repeated at least 3 times and the experiment should be repeated at least twice to get better result. It can be minimized the error and the variance from the result will be minimized by this. Okay, that's all. Thank you for